What if I told you a random crack in a Martian rock could rewrite what we think about Mars? Today, we're diving into a discovery that sounds almost cinematic. Curiosity rolled over a humble rock in Gediz Vallis Channel, and when it cracked, the inside revealed pure elemental sulfur, brimstone. Not just a little sulfur, but a surprising, high-purity bloom of sulfur crystals staring back at us from the red planet. And yes, this is not typical. Sulfides have shown up on Mars plenty of times, but elemental sulfur? That's a different ballgame, and it's got scientists circling back to rethink how Mars's geologic story unfolded. Let me set the stage with the vibe of this moment. Imagine wandering through a dusty landscape, and your rover, this high-tech, stubborn compass of human curiosity, stomps on a rock, the crust splits, and suddenly you're looking at a treasure map written in yellow crystals. That image matters because it challenges a few long-held assumptions about Martian chemistry and the processes that can concentrate sulfur in its pure form. Personally, I think the most exciting part isn't just finding sulfur. It's realizing we might be looking at a set of conditions that can produce or preserve elemental sulfur on the surface in amounts that are more than a curiosity. First big idea: the difference between sulfides and elemental sulfur. Sulfides on Mars are like footprints left by water, signs that water moved through minerals, dried up, and left salts behind. Those tell us about past watery environments and climate. Elemental sulfur, by contrast, is a rarer, more direct indicator of sulfur-rich chemistry that doesn't require the same evaporating water setup to reveal itself. What this matters for, in my opinion, is how we model sulfur cycles on Mars. If you're staring at a field of pure sulfur rocks rather than salts, you're staring at a different kind of geological recipe, one that hints at unique sulfur sources, oxidation states, or volcanic or intrusive histories that can concentrate sulfur without relying on long, watery evaporites. What people don't realize is that this isn't just a more sulfur. It's a potential clue about isolation pockets where sulfur could persist or form under Martian conditions that aren't our Earth-centric expectations. Second big idea: how did this sulfur get there, and what does it imply about Mars's past? The region is old terrain carved by a river network billions of years ago, yet the sulfur seems to be perched on or near the surface in a way that doesn't neatly fit simple evaporation models. From my perspective, the key takeaway is that Mars isn't a straightforward sandbox with one climate story. The presence of near-surface elemental sulfur opens up questions about geological processes that can accumulate or expose native sulfur, possibly through volcanic off-gassing, hydrothermal activity, or unusual mineral associations. If you take a step back and think about it, you're confronted with a bigger trend. Mars's surface reveals episodic, localized chemistry that can surprise even seasoned planetary scientists. This raises a deeper question about how much we've generalized Mars's history from broadly sulfur-bearing rocks to a single, simple timeline. A detail I find fascinating is that the sulfur here could be a piece of a much larger, more complex sulfur story that we haven't mapped yet across other channels and valleys. Third big idea: the implications for life detection context. Sulfur is essential for life on Earth, integral to amino acids and proteins. But sulfur's presence on Mars, especially in elemental form, doesn't equate to life. It does, however, emphasize that Mars hosted chemistry ripe for biological interactions in the past, or at least chemistry that could support life's chemical precursors if other conditions aligned. What this really suggests is that our search for life should broaden its toolkit, not only looking for water-rich pasts or organic molecules but also cataloging unusual mineral chemistries that could feed or hint at biological pathways in different environmental niches. What many people don't realize is that a single finding like this can reframe where we search and what we look for, by highlighting uncommon but scientifically meaningful in-mineral environments as potential targets for future rovers or sample return missions. Fourth big idea: the practical science and next steps. The scientists' move now is to model how such sulfur could arise in Gediz valleys given Mars's climate evolution, rock types, and hydrology. This isn't a tidy answer. It's a call for deeper modeling, more data, and perhaps targeted follow-ups that could include drilling or sampling adjacent rocks to see how widespread the sulfur signature is. From my view, the exciting thing here is the iterative nature of planetary science. A fortunate crush reveals a mystery, researchers refine hypotheses, more data either narrow the possibilities or open new doors. If you think about it, this is how we turn a single meteorological-like anomaly into a narrative about a planet's geologic and perhaps even habitable potential. A detail I find fascinating is how a rock's misfortune, getting crushed under curiosity's wheels, becomes the catalyst for a cascade of scientific investigation. Deeper insight, broader patterns and the human element. This discovery underscores a recurring theme in space exploration. Serendipity often drives the best questions. The Gediz Vallis Channel itself is a chronicle of an ancient waterway, and the sulfur find adds a new page to that chronicle, one that invites reinterpretation of how water, heat, chemistry, and rock interact on Mars. What this really signals is that Mars's surface is a dynamic laboratory where rare mineralogical states can exist and be exposed by chance. It also highlights the perseverance of our robotic explorers, their suite of instruments, their ability to withstand harsh terrain, and their capacity to turn a small crack into a big scientific moment. In my opinion, this is a reminder that discovery isn't always about sweeping grand theories. Sometimes it's about noticing the unusual grain of a rock and asking, what hidden conditions could produce this? Closing thought, what comes next? And what does it all mean for humanity's long-term exploration? If this elemental sulfur story is the opening act, the next scenes will be about where those sulfur-rich pockets exist, how widespread they are, and what that tells us about Mars's geologic and possibly climatic diversity. The broader trend is clear. As we push deeper into Mars, we're likely to encounter more surprising chemistry that challenges Earth-centric models. For the audience, if you're rooting for a definitive sign of life, this is not that signal yet. But if you're chasing the unknowns of planetary geology and the hints they offer about habitability, this is exactly the kind of breadcrumb you want to follow. So, what's your take? Do you think elemental sulfur on Mars could imply overlooked volcanic or hydrothermal activity, or might it point to an entirely different sulfur cycle on the red planet? I'd love to hear your theories in the comments.